We're going to go ahead and get started. Thank you all for joining us at this Thursday town hall. The Q&A panel with the Dragonfly team. It was at AbSciCon, the last AbSciCon, that we learned that Dragonfly was selected as the next New Frontiers mission. So I was reminiscing a lot about the last AbSciCon this morning as I was preparing for this panel. So in that spirit and wanting to make sure that this mission that's going to be really pioneering our understanding of prebiotic chemistry and astrobiology reflects the astrobiology community, we want to make sure that we're fostering dialogue between the team and the broader community. So that's the purpose of today. And to put that in even fewer words, please ask us your questions. We want to have a discussion today and use this time to build. So without any further ado, I'm going to turn it over to the principal investigator of Dragonfly, Zibby Turtle, who's going to kick us off.
Okay. Thank you, Shannon. And thanks everyone for being here today. I'm going to start with just a very brief, hopefully, overview of Dragonfly and what we want to do at Titan for people who aren't already familiar with the mission. But we really do, as Shannon said, want this to be a conversation. So we're going to keep that short and then open it up for questions. Right, so Titan is a moon of Saturn. It's a very unique moon in our solar system in that it has a dense atmosphere, and it gives us an opportunity, a number of opportunities. Scientifically, it gives us a place to look for answers to aspects of what makes targets in the solar system, especially the outer solar system, habitable, and what are the chemical processes what chemical processes are happening there, and what can they tell us about the chemical processes that happened here early on in the history of Earth. And of course, we all have the question as to whether life has developed elsewhere in our solar system. Right, so Titan is the surface gravity is 1/7 the gravity here. That will come into play in a couple more slides. The surface temperature is a balmy 94 Kelvin. It is not a warm place. Being an icy satellite, the bedrock composition is water ice. And like many of the moons in the outer solar system, it's an ocean world with a deep interior liquid water ocean. It has an atmospheric composition that is mostly nitrogen with a little bit of methane, which chemically makes things super interesting. And the surface atmospheric pressure is actually higher than the atmospheric pressure here, which will also come into play in a couple slides. So there is the photochemistry in the upper atmosphere produces very complex carbon compounds, and this material falls out through the atmosphere and covers the surface. And this is the reason that Titan gives us such a cool opportunity, because the organics on the surface of Titan have had the opportunity in Titan's past to mix with liquid water at the surface. If there's melting at a site of a cryovolcano, possibly, certainly at sites of impact cratering, where the surface will be melted and stay melted for extended periods of time. So that's one of the key aspects that makes it such an interesting target from an astrobiological perspective. All right, so I mentioned that the gravity and the atmospheric density were going to come into play. Because we have higher atmospheric pressure and density at Titan, and lower gravity, it's actually physically easier to fly at Titan than it is here at Earth. And so that gives us the opportunity to take advantage of the atmosphere, not only for its chemistry, but also as a means of transport, of traveling across Titan. So like the Mars rovers, we bring everything with us from place to place, but on Titan, we're able to fly rather than drive. The schedule for the mission is we launch in 2027. This gets us to Titan by 2034, where we'll explore for over 3 years, traveling up to 180 kilometers, depending on where we land in our landing ellipse, to explore the deposits associated with this impact crater. Titan is a really Earth-like place in terms of its geology, even though the materials are very different. Titan's equatorial region, these dark areas around the equator, are actually dunes. They're organic sand dunes, which are fascinating in and of themselves. And so this area gives us the opportunity to explore a variety of different geologic settings and sample a variety of different materials from this organic sand, from water ice, rich interdune materials, and then deposits associated with the impact crater where organics and liquid water may have mixed, as I said, for possibly extended periods of time. So the focus of our mission is prebiotic chemistry. We want to know what chemical components are available on Titan's surface and what processes are at work and whether they're producing biologically relevant compounds. And then we want to put that into the context of the habitability of Titan as a system. The methane cycle in its atmosphere, the organic cycle, the processes that move, transport, modify, and mix materials on the surface, and that mix them with liquid reservoirs. We not only have had the opportunity to mix with liquid water, Titan's surface, and in Titan's interior, possibly in that deep ocean, but there's also methane in the methane in Titan's system has a cycle like our water cycle. So methane actually forms clouds and rain and lakes and rivers and seas on Titan. And so there's the opportunity that methane could support exotic biological systems. So we have a suite of instruments. We have a mass spectrometer, sampling system called Draco, and then we have a geophysics and meteorology package with a suite of sensors to measure aspects of the environment. We have a camera suite, and we have a gamma ray and neutron spectrometer. So with these instruments, we'll do a detailed investigation of the not only the composition of surface materials at landing sites, but also putting those into the context of Titan. So the gamma ray and neutron spectrometer gives us information about elemental abundances in the surface underneath the lander. And then the mass spectrometer gives us an inventory of the organics, which we can use to look for different aspects of the surface materials. So we have the opportunity to identify potential biomolecular components, to look for patterns of complexity within the materials we sample on the surface, to identify whether there is an enantiomeric preference, and to understand a number of, or to make measurements relevant to a number of chemical biosignatures. With the DragMet system, we have the ability to monitor atmospheric temperature, pressure, wind speed, et cetera, and to make measurements of different aspects of the regolith, the thermal response, understanding its porosity. And we have the capability, potentially, to detect aspects of the subsurface. So we have seismometers that can, or we have a seismometer and some geophones that will be able to listen to understand the level of seismic activity on Titan, and as well as E-field measurements, electric field measurements that will be able to inform us about the Schumann resonance. And then with the suite of cameras, we have the ability to take panoramas around the landscape around the lander. We have forward and downward cameras that will image not only on the surface, but while we're flying, so we'll have aerial imagery of Titan. And we have microscopic imagers that are designed to get very high resolution imaging of the sampling sites where the sampling system, the pneumatic drills will pick up, or the rotary percussive drills will pick up materials to transfer into the mass spectrometer via a pneumatic system. And the image here is just showing simulated, well, lab tests, illumination of similar Titan materials with different LEDs that we have on board to illuminate the surface at Titan. So I know that was a really brief overview, but like I said, we really wanted to focus the time here on questions. We're happy to go into more detail about different aspects of Dragonfly and what we'll do at Titan. So I wanted to introduce the panel. Shannon McKenzie, who you've already met, as our moderator, is our assistant project scientist. Jason Barnes is one of the deputy principal investigators. Melissa Trainer is the other deputy principal investigator, as well as the lead for the mass spectrometer, the DRAMS instrument. And Ken Hibbard, who is hopefully online from APL, is our mission systems engineer. I also wanted to mention that, of course, any mission like this is the product of a very large group of people, and many of those people are here in the room with us today. And if, when we're doing the questions and answers, if people on the Dragonfly team have answers to questions or want to chime in response, just wave your hand or go up to the microphone. Like I said, we really want this to be a dialogue and a conversation. Thank you.
Thanks, Zibby, for getting us all on the same page, since we realized not everyone probably had time to come to all of the Titan Talks on Tuesday. So hopefully now we're all ready and primed to dive into Dragonfly. I will also be monitoring the Vimeo chat for people who are online. So folks online can also ask questions. So come on up. If you have a question, come on up to the mics. We've got one over here, one over here. Oh, and we have one already. I don't even have to kick it off. Thanks.
Thank you. My question's more from the engineering perspective, but I was wondering what sorts of things do you have to do to combat the cold temperatures of Titan for the Dragonfly mission?
Do we have Ken online?
Yep.
Oh,
there's Ken.
Jalen Shawcross, Bellarmine Prep.
Thank you.
Go ahead, Ken. Take it away.
Can you folks hear me?
Yep.
Okay. So I think I heard the question is, what do we have to do to combat the thermal environment?
Yes.
So it's challenging. So Titan's very cold, as many of you, I assume, know. And so some of the things we're doing is the lander down on the surface is entirely encapsulated in foam. And we use the waste heat from the MMRTG and distribute that within the lander body to keep everything warm. So the RTG puts out about 2,000 watts of thermal waste heat. And so we circulate that using a forced convection system, move that heat throughout the lander, and try to maintain kind of a nominal environment for the internal electronics. Anything that lives outside of the lander is being deliberately designed to survive and then perform in the cryogenic environment. So everything has to be able to survive at 94 Kelvin if it lives outside the body. And then we will preheat motors and drills and things like that into an operational range before we use them. And then while we use them, maintain them warm and let them cool back off when they're not in use. So it is quite the challenging design.
That's very cool. Thank you. Much appreciated.
My pleasure.
Thanks, Ken. We've got another question in the room.
Hi, my name is Hirai from Tokyo Institute of Technology. And my question is concerning for the research target. My question is, can we access 5 micrometeorite deposit or nickel evaporites? Because it is also important for organic chemistry due to concentration and polymerization of organics. And there are very large deposits like Hotte and Chui region, but this region is very, very far from the landing site. So do you have any idea or plan to access these organic materials?
Jason, I think that's a question for you. Yep.
Yes, as you point out, we're not landing near the evaporites, but we're still very interested in them. Of course, our imaging of Titan is pretty coarse, and so we only have pixels that are a kilometer in size. There very well may be evaporite outcrops that are smaller than that we will be able to have access to. But our primary research focus for organics will be those sand dunes. We'll be landing within the sand dune region. And it turns out, and I didn't know this because I wasn't a geologist, turns out sand dunes on Earth are not all covered in sand, okay? In fact, the Namib Desert in Southwest Africa, for instance, is 40% covered in sand dunes. And in between are these sand-free interdunes. So we'll be accessing water in the sand-free interdunes, water ice, and then we'll be able to fly over to the sand dunes, which are made of organics and may ultimately derive from the evaporites. We don't know. and we'll be accessing those for sure. And we will be able to, hopefully, if we see any evaporites along the way, we'll be able to stop and sample them. But you're right, we're not going to be able to get into the large evaporite deposits.
Thank you.
Although I will just add that I am crossing all of my fingers and toes that we're going to come across some kind of playa in the interdunes and we can taste those evaporites and figure out what they are. And then you and I are going to write a cool paper about it. Thanks. All right, we'll take one more from this side.
Oh, hello. Hi. My name is Natalie Gruffenstedt. I'm a postdoc at the Santa Fe Institute and Blue Marble Space Institute of Science, and very excited about this mission. My question's related to the life detection aspect of this. So as you mentioned, we're kind of intuitively thinking that if we do come across life or protobiological systems there, they'd be very different from life on Earth because of cool, interesting chemistry thing, sorry, cutting in and out, that's happening there. So, and the question is about how are you integrating that, the fact that it might be so different with looking for questions about habitability or life detection? And are you planning on doing that in-house within the team or expecting to collaborate with the rest of the community on that? And if you are, how can we help and what are you wanting from the community and from funding sources to keep this work going?
You hear me? Yeah. So thanks for your question. One thing we do want to emphasize is that Dragonfly is not a life detection mission. That is not our goal, right? Our goal is to understand prebiotic chemistry. So we're very interested in looking at the composition of the areas of the Titan surface that we're exploring, as well as how that chemistry has advanced towards something that might look familiar to us as a potential biochemistry, right? So but to kind of pivot from your question, though, what is related is, well, how will we interpret the molecules we find and whether or not they could be either potentially prebiotic or perhaps, maybe even chemical biosignatures. And so the way we'll do that, of course, we're targeting molecules that would be very familiar to us from life on Earth, things like amino acids and nucleobases, things we suspect could be forming during aqueous processing on the surface. But a lot of how we interpret the information that we get back is going to be how we answer some of these questions. So we look at different patterns of molecules that we may find and try to understand if there's perhaps a distribution that we wouldn't predict from abiotic chemistry. Or we'll look at if we're lucky and we find amino acids and we measure their chirality and we see a big enhancement of one enantiomer over another. So we'll be looking at those things and then we'll be understanding how to interpret them in the context. And I do want to say, I'm sure I speak for everyone, I mean, we're going to want the whole input and the full understanding of the whole science community on how we interpret the types of data that we find with that and all of the advancement. I mean, we're landing in by 2034, right? So even by then we may have a lot of great work is being done in this area in understanding how to interpret some of the chemicals that we're finding.
Yeah.
Did you want to add something?
I just wanted to add from a programmatic perspective, the expectation, NASA said that they will do a participating scientist call for Dragonfly. The expectation is that will be in Phase E, although if they want to do that earlier, that would be excellent. So we're really looking forward to a participating scientist program for the mission. I would hope that there would also be a New Frontiers data analysis program within NASA. That's typically one of the ways they've done funding for mission data analysis. So we would hope there'd be something like that as well in the future. So there should be opportunities, and we'll keep working with NASA to understand what they'll be able to do on that side.
Great, thank you.
All right, let's jump to the other side of the room.
My name is Garrett Roberts-Kingman. I'm a postdoc at Ames Research Center. I was wondering if you could speak a little bit more about limits on the upper bounds of molecular sizes that can be definitively identified by the mass spec and other instruments.
Sorry, I just want to make sure I understood the question. Did you ask about the mass range of the mass spectrometer?
Yes.
Okay, sure. Yeah. So the mass spectrometer operates in two different modes when we're looking at solid samples that we're analyzing from the surface. One of these is a laser desorption and ionization mode. And in that, we have a requirement to measure up to 550 Daltons mass units, but we actually, right now we're showing performance up to almost 2,000. And so we'll have a very wide mass range we expect to be able to probe with the surface samples, and they would be minimally processed, just processed by the sampling system and delivered to us, and then we'll be looking at the molecules that are in those samples. When we operate in our gas chromatography mode is our other mode, GCMS, and that's where we can do a more selective separation of some of the compounds we find, looking for things like amino acids and separating perhaps chiral pairs. And in that case, we have a lower mass range, but that's partly imposed not just by the mass spectrometer actually, but just the ability to get molecules through the gas processing system, and they have to be volatile enough to sail through. And then it's, again, there's a requirement of about 260 Daltons, but a capability that goes up above depending on the compounds that we find.
So thank you.
Please.
Hi, my name is Lu Chao. I'm a postdoc at NASA Goddard. And my question is, so I understand that Dragonfly is not supposed to be a life detection mission, but I couldn't help noticing that one of the objectives states that to search or understand the potential existence of hydrocarbon-based life. Could you speak a little bit more about how going to the dunes is going to be affected, or how that's going to affect what you're going to see, depending on where this potential hydrocarbon-based life could be? Because I would imagine them existing in the lakes, and we're not going to the lakes, and how you interpret the data that could be coming from these potential really exotic biosignatures, which is super, super interesting.
Do you want to take that, Jason?
Sure. So you're right in that presumably any hydrocarbon-based life is going to be primarily based in the lakes. We will be sampling the sand dunes, which are a primary organic sink for Titan. A lot of the organics that are produced in the atmosphere and are processed in some way in order to produce those sand dunes. And they, in fact, may be processed within the lakes themselves, either by coagulating smaller particles or by producing evaporites and then blowing them out. So you're right in that we won't be directly sampling the lakes, but we will be sampling a lot of the organic material, and in fact, the bulk of the organic material that's been on Titan, and that may be able to allow us to sort of provide a remote sample, essentially, by sampling those sand dunes. Now, we don't know that they come from the lakes, but once we measure them, we hope to know the answer after that.
And briefly, I did want to talk to one of the reasons we're not going to the lakes and seas, because they're obviously a really fascinating target. If you noticed in the video, you saw the high gain antenna deploy. Because we don't have a fleet of orbiters at Titan, sadly, the way we do at Mars. Dragonfly does direct-to-Earth communication from the surface of Titan. And at the time of year when we will arrive, it will be northern winter. So the North Pole will be, the northern North Polar region will be in darkness, just the way our North Pole is during the winter, because the sun won't be up in the sky, which means the Earth won't be up in the sky either. So we wouldn't be able to do direct Earth communication from the North Pole at this season on Titan. So this gives us access to this destination at the lower latitudes, gives us access to a crater where water and organics may have mixed. But as Jason alluded to, we're kind of depending on the transport of materials that may contain biosignatures from other places on Titan for possible methane-based systems.
But also just understanding, what materials are available for chemistry, whatever prefix you want to put on that, on the surface of Titan. We don't know that yet. We will in the 2030s, but we don't know it yet. And so providing that really critical input on, what's available to play with on the surface, I think will have implications even tens of degrees latitude southward.
Thank you.
Great. We'll come over here.
Hi, Ben Hurwitz at Georgia Tech. You mentioned something about atmospheric and sampling the atmosphere. How high is Dragonfly going, and is there capability of actually sampling while you're flying at night?
So there are different aspects of the atmosphere that we'll be measuring. So we can do with the meteorology sensors, we'll be able to do measurements in flight. And we actually intend to do some profiling flights to get measurements at different altitudes in the lower atmosphere. Those will only go up to an altitude of a few kilometers because the primary goal of the mission isn't the atmospheric sampling, but of course it's fascinating and something we want to try to do even if it's at the lower part of the atmosphere. But in terms of measuring the noble gases, the atmospheric inlet to the DRAMS instrument, those measurements were made at the surface.
Thank you.
Did that answer the question?
Yep.
Okay.
Thanks. Turn it over to this side of the room.
Hi, Martin Rahm, Chalmers University. I have an engineering question actually. I was hoping you could speak to the degree of automation that will be engineered into Dragonfly. How will it be responding in case it loses contact, or if it's sense that it's about to tip over or sink or something?
Ken, did you hear the question?
I did. So we use some level of autonomy when we fly the system, right? So the round trip flight time to Titan could be as long as 3 hours. So obviously when we're traversing on the surface, you can't fly by joystick. And so the system has to be able to autonomously move from point to point. It has a predefined flight sequence, if you will, and the ground will load up destinations, cruise altitude, things like that. And so then the system largely executes that onboard flight plan that has been kind of rehearsed and tested and verified on the ground. So I view it as a set of parameters that you upload flight to flight, but then in general, we execute a very similar flight plan every time. The navigation is done with image-to-image correlation. So because we don't have a detailed DEM of the Titan surface a priori, we track features in one image and compare it to features in a subsequent image where there's overlap. And so we use that image-to-image correlation to navigate. Our goal is kind of bulk navigation, not precision. So perhaps an analogy for anybody who's a small aircraft pilot, often when you're learning to fly, you navigate by following a highway beneath you. It doesn't really matter if you're to the right of the highway or the left of the highway. You just want to know that you're going in the right general direction. And when we look to land, we use both the onboard cameras and the LiDAR system to look for a safe landing zone, which we've defined as a slope less than 10 degrees and 8 to 10 meters diameter, absent of any hazards, where a hazard is anything larger than a 1/4 meter scale rock. And in terms of landing precision, imagine you're landing in an empty parking lot. We want to set down safely in the parking lot. I don't care what specific spot I'm in, if that makes sense, as long as it meets our safety criteria. And so that's in terms of the surface navigation. The rest of the operations take place when we are on the surface stable. And so they're really similar to most any other robotic mission. There'll be a set of onboard preloaded time tag sequences, and those will execute macros within the different instruments and between the different instruments that coordinates specific measurements and activities on board the lander happening on a time-based system. We do have an autonomy rule engine on board. This is derived from our historical autonomy system we've used on a lot of our past missions, which is a set of onboard monitoring. We track telemetry and all the data indicators we have in the vehicle. And then when we detect anomalous behavior, there's a set of predefined responses that are also done via command macros. So that's largely the extent of the automation we have. And then there are safeguards in the design to prevent things like tipping over or things like that. It's not so much a real-time response. It's more making sure the design ahead of time is robust to those kinds of threats or faults.
Okay, thank you. But if it loses contact, it won't fly back or something to it previously working?
No, we don't need contact with the Earth during the surface flights. We intend to have contact on a best effort basis, mostly because they're critical events to us and we want to have monitoring, but communications with the Earth is not required during the surface flights. And again, once we land on the surface, if we lose contact with the Earth, we have a scheme on board to search for signal coming from the Earth. And worst case, if we lose all knowledge of our inertial reference position, the Earth is largely co-aligned with the sun. So if we can figure out where the sun is, we can figure out where the Earth is and reestablish calm.
Thank you.
Thanks. All right, take it away, Mike.
Hey, Mike Malaska, JPL. So I had a question on the dune growth mechanisms that y'all were investigating. So one of the questions that we Titan community was how the dunes sands grow and whether they were all like tiny little chunks of a major eroded piece or if they were somehow coated and you had like a series of concentric layers being built up. In your sampling system, do you have a way to be able to deconvolve those two possibilities? Like, do you have the ability to do like hold on to a grain and do successive laser ablation and GC mass spec of that?
So I'll answer the part about the sampling system and the mass spectrometer, and then I'll let other people weigh in on the kind of imaging and other measurements that we can do to help with this question. So the short answer is no. So the way that the sampling system works is that we either ingest already, particulate matter, or we use the rotary percussive field to generate particulate matter that then gets pneumatically transferred into the sampling cup. And so we're not presenting like a fresh rock face or a core, right? We're already sort of homogenized it to some extent. And so we are looking for variation in the sample when we do laser desorption mass spectrometry, but we won't be correlating it with the spatial information in the sample so much as we'll just kind of scan across the face that is in front of us just to look for variations without being able to correlate it to a location on a particular, depth or something, depth profile. So that's the answer about the sampling system, but there's other things that we can do to learn about the dunes. So.
Yeah, our microscopic imager will have very small pixels, and we'll be able to resolve individual sand grains. And so we hope to at least be able to see their size, whether or not they're built from smaller material or where they're singlethic chunks, and their roundedness to try to ascertain how far they may have traveled. So that's how we're going to try to get a handle on what you're doing.
And the gamma ray neutron spectrometer will give us the bulk elemental composition. And so with the context of the other information, we may be able to understand aspects of that as well. So if we're in a situation, for example, where there's organic material mantling water ice, we may be able to measure, the shallow depth to that water ice. But if we know we're on a deep plinth of sand and we're still seeing water ice, then that would be indicative that there are water ice cores, for example, in the sand grains. So there are a number of ways we have at getting at it, but it's going to be kind of a systemic process to combine the different data sets.
And one last, with your imaging system, if you did see like some of the grains have been chipped and revealing a coating, about what's the resolution scale of a coating that you'd be able to see, you think?
The resolution of the microscope.
I mean, we don't actually, if it's a coating, it's going to be everywhere, right? You'd have to cross-section it.
I'm assuming there's a chip.
If you somehow had a cross-section, the pixels are going to be of order 60 microns. So, 100 microns, 150 microns, depending on what the contrast is between the material inside and the material outside.
Thank you.
Hi, I'm Francesca Carey. I'm from the University of Hawaii at Manoa.
Can you speak a little closer into the mic?
Is this better?
Yes, thank you.
Great, thank you. Francesca Carey from the University of Hawaii at Manoa. So if one of your primary interests is analyzing prebiotic chemistry at the surface, I was wondering if there's anything you're hoping to learn from Dragonfly about how chemistry fundamentally operates in a cryogenic temperature regime to sort of understand how these prebiotic molecules of interest have changed over time.
Thanks. That's a great question that I think Melissa probably wants to answer.
I'm going to apologize. I just want to apologize to everyone in the room. I don't know. I'm having a lot of trouble understanding some of the questions coming from the speakers. The audio at the table here is not great. I think it's better for people online. So do you mind repeating the second half of the question, just the question?
Yes, of course. So the second part of the question was how we might be able to better understand how chemistry itself operates at cryogenic temperatures so that we can better understand how the prebiotic chemistry and the molecules you're interested in have changed over time?
Okay, yes. Okay. So I'll give a little bit of an answer to that question. I mean, some of that has already come from scientific research that has taken place over decades that led us to the point to even, hypothesize that we could see this kind of hydrolysis on the Titan surface if there are melt pools, for example, and the organics from the atmosphere can be hydrolyzed or react in other ways to form the kind of molecules we're interested in. So a lot of that has come from laboratory-based work, and I expect it to continue. There's some projects looking at, even just this week, I've seen some great work on that. Like what kind of chemistry do you expect in a melt pool of a crater environment, modeling and laboratory research, and how those things could form potentially, and then evolve. I mean, once the ice is frozen, we're kind of assuming that the molecules are then fairly static and are not continuing to degrade. There's not really a lot of radiation or anything on the surface. And then other types of chemistries that could be taking place. Again, a lot of what we're understanding is based on laboratory research that has been going and will continue to go, and is very complementary. Oh, you want to answer, Morgan? Oh, yeah. I mean, I'm going to pass it over to one of our co-Is, Morgan, who is happy to jump in and take over from me babbling.
Well, you were doing a fantastic job, so I don't think. How's this? Is this better?
Yes.
Okay.
Great, yeah.
You were doing a great job, Melissa, but yeah, there's a really impressive community of organic chemists, cryogenic experts that are all working on a lot of laboratory experiments to be able to inform and interpret the data. But as Zibby pointed out, a data analysis program to follow would be a really important component as well. I'd also like to point out that we have a student investigator program that there's a deadline coming up. I believe it's May 27th. That program is more targeted for students who aren't already connected to a mission and would like to get that kind of experience. And some of the research that we're doing as part of that program is to help inform some of those measurements.
Thank you. Thanks, Morgan.
And just to further plug the guest investigator program, if you are a graduate student without connections already to planetary science and planetary science missions, if you go to the Dragonfly team website, so just Google Dragonfly Titan, unfortunately, you do have to add an extra qualifier because there are other dragonflies out there. And then at the top of the page, it says student opportunities, and you'll get all the information that you need there. Great. Thanks, Morgan.
Hi, Brady O'Connor from McGill University. I was just curious to know how robust the drill is going to be because you guys we don't know all the types of samples or the types of material that we're going to discover. So how robust is that drill to be able to get samples if, let's say, we see water ice mixed with sand or just a sand core, like things like that? I was wondering if you could comment on that.
That's a great question, and we are very lucky to have one of the representatives from our drill team here, Catherine Bywaters, who will help answer. Because our fundamental question is, what is on the surface of Titan? How do you design a drill when you don't know what the surface is that you're going to go sample? Take it away, Catherine.
So Honeybee has a great motto that you test as
Can you
fly.
step a little closer to the mic?
Okay, is this better?
Yeah, thanks.
Okay. So Honeybee has a great motto, test as you fly. So we do a lot of work with making different simulations, testing, as well as testing with everything that we can find here on Earth, different types of basalts, which are very difficult to drill into. So it really comes down to a lot of testing in simulated fill, as well as other materials that are known to be, some of the hardest that you find here on Earth. So I think that's the long and the short of it.
So what if we encounter something that's very hard? Well, we test with basalt. What if some of these organics are kind of sticky? Well, we add some oil and some walnut shells together and see how that gets handled by the Draco system.
So it is being designed to be as wet as possible.
Right, as robust as possible with all of the different conditions that we can think of. Like you said, walnut shavings and different oils and different materials to
characterize how it's going to handle and make sure that we can at least acquire enough sample for analysis.
Thank you.
And I'll just add to that, if I may, which is that we also have a lot of analysis of the surface environment that we're going to be doing before we even make the decision to drill. And if we suspect that there is a material that is there that is maybe too sticky and would completely gum up the drill, or if we do it, we're going to do a pilot drill hole. If we do decide to move forward, and if we get data back that indicates that maybe that surface is out of the bounds of what we had imagined and therefore might be problematic, we're not required to drill at every single location. And so we'll also be making those decisions with ground in the loop as to whether or not a sample, we're going to be able to drill and sample.
And also another good point is we have two, right?
Yeah.
So there's two drills. So if one does fail, it's not, we have a backup.
Sorry, just quickly, how deep will the drill be able to get samples from?
I think that's 6 centimeters, like below the skin that you see.
Okay.
So still not a deep.
Thanks.
Hi, Christoph Richmond from Stone Aerospace. I was wondering what kind of weather we expect on Titan, and can Dragonfly handle a rainstorm or a sandstorm?
Right, so we absolutely have to be aware of the Titan weather. So Titan's year is 29 and a half years long. And with Cassini, when Cassini was in orbit around Saturn, it got to observe the seasonal cycle on Titan for 13 years. So we saw almost half of a Titan year. Dragonfly will be arriving basically one Titan year after the beginning of the Cassini mission. And when Cassini arrived, it was southern summer. When Dragonfly arrives, it will be southern summer. So at that season, most of the cloud activity was at the South Pole. And so we'll be at the low latitudes. We did not see weather, cloud systems or rain near the low latitudes until a year after the northern vernal equinox with Cassini. So we wouldn't expect there to be clouds or rain or storms at the latitudes we're exploring until several years after we arrive. But weather doesn't always do what it's predicted to do. And so we do need to make sure that Dragonfly as a system is robust to methane rain, et cetera, if it were to rain while we're during the nominal mission. The flights themselves are short. I don't think I got into this in the overview, but the plan is to fly basically every other Titan day, which is once a month. And the flight itself will be about 30 minutes. So we can change that depending, if it turned out that the weather sensors indicated there was rain or high wind or something like that, we wouldn't fly, and we don't expect the weather to change on the kind of half-hour time scale at Titan. So we would know before we flew and make a decision based on that not to fly if the weather conditions were adverse, and we'd just stay on the surface.
We're going to take one of our online questions next. I'm going to bring my laptop up here so I read it correctly. If organics are sticky, are there any potential issues with cross-contamination or carryover in the sampling system?
Okay, so again, the question is about if we have, because I mentioned sticky organics and potential cross-contamination. So what we've done is we've set a requirement to minimize cross-contamination as much as possible. You can't levy a perfect, completely restricting cross-contamination, but to reduce it as much as possible. We have a couple ways that we can deal with that in the sampling system. One is that because it's a pneumatic system, and because we're actually flushing a lot of material through every time, a lot more than we necessarily are capturing for a sample. And so we have the ability to flush the lines with a little bit of new sample as well to make sure that you're kind of getting rid of any residual material from a previous run. Similarly, the drill has a percussive aspect, and it can kind of shake itself a little bit and help clean off the material on the drill as well. And again, just the nature of the pneumatic system and why we wanted to do that is it's a lot less likely to have material sticking to the sides than with a scoop, for example. And that was a choice that we made, partly to help with the fact that we know there's a wide range of materials and a wide range of material properties, and to limit things like cross-contamination. And then another thing we do is that for the LDMS analysis, we have single-use cups. And so each time we take a sample, it's a fresh new cup, and that's another way that we can address that concern.
Thanks, Melissa. We'll come back to the room.
Hello, I'm Katerina Yoakum. I'm an NPP at NASA Goddard, and I'm really curious about the GCMS measurements because, Melissa, you said that, of course, they have to be volatile, and at 95 Kelvin, amino acids certainly will not be in the gas phase. So what are the target molecules, and what do you hope to search for the enantiomeric assets?
Yes, thank you so much. So the requirement for them to be volatile is for them to be volatile in our analysis, which, but we don't want them to be volatile on the surface. We want them to be solid or stable on the surface so that we can sample them. So the samples are kept very cold through the pneumatic transfer system. And then once they are captured in a sample cup, we still try to keep them well below the freezing point of water or the paratectic point of, for example, a water ammonia mixture, to try to preserve the bulk solid, depending on where we're sampling. But then for the GCMS analysis, the next step is that we heat them up deliberately, right, to volatilize and drive off materials. And we can do that to either directly measure molecules that in a pyrolysis mode that are able to evolve up to about 600 degrees Celsius.
Okay.
And so then we can see things like, alcohols and amines and lots of different components. But then we also carry the ability to do a chemical derivatization. And that's the way that we're going to target things like amino acids. And so the derivatization happens inside the cup in the oven. It's a single step, and this is something that has been done before, for example, on Mars with the SAM instrument on Curiosity. And that allows us to sort of do a chemical substitution. Now you've made a molecule that is less polar and is more volatile and is able to pass through the GC system.
So beyond amino acids, are there any other forms of molecules that you're searching for?
Yeah, sure. I mean, we're looking for whatever we can see, right?
Okay.
So targets that are mentioned in our high level requirements are things like amino acids and nucleobases. We're interested in seeing if there's fatty acids there. Things that would be of interest for biochemistry. And Morgan, are you wanting to add? Okay. We're certainly expecting to see lots of aromatics, pHs, based on our understanding of the chemistry that happens in the atmosphere. Amines. I mean, we could go on and on. I could talk to you offline sometime.
And just a quick reminder that that's one of the benefits of having mass spectrometry, because it's such an agnostic technique when it comes to, of course, the molecules have to be volatilized. They have to have a charge, but otherwise we're relatively agnostic compared to other techniques. So that's that's the reason why it was selected.
Preach, Morgan. All right, let's take the next question from this side.
Hey, I'm Hiro at JPL. I am an ignorant engineer asking a stupid question, so bear with me.
No stupid questions in this room.
But I am super excited about it. So I understand that the landing site is at the lower latitude. Just curious, is there any possibility long term to visit all the way to the lakes?
It's a pretty long way to the northern lakes. The nominal mission is defined a 3.3 years is defined by the time scale to get from the because the landing ellipse is reasonably large because of the dispersion in Titan's atmosphere. So the nominal time scale is set to allow us to get from places within that landing ellipse into the deposits associated with the crater to make the key measurements of the chemistry of those materials. Because we were designed to be powered by an MMRTG, the limiting factor on the lifetime of the mission is the heat output from the MMRTG, and that is longer, but than the 3.3 years, possibly by a factor of 2 or so. So there is hopefully the possibility for an extended mission of some sort, but whether one could get that far is I think that would be a long shot. And we'll probably find a lot of other things that we want to explore in the nearer area to expand upon questions that are raised by the measurements we make. So I think we're going to have to leave the northern lakes and seas for a future mission.
I'm still hoping for some sub-Cassini resolution
Yeah.
little lakes at latitudes we
Some
might
of
be able to.
There is evidence in some places of possible, temperate latitude lakes. And as you say, there might be playas or things like that in and among the dunes. We've definitely seen rainfall, evidence of rainfall at these low latitudes. So we know that there is moisture there at some times of year. Even the Huygens probe, when it landed at low latitude in the southern summer, there was moisture in the material at the landing site of the Huygens probe. So there are certainly surprises that await, and maybe we'll be able to make some measurements in the local vicinity.
Thanks, super exciting.
Thank you. Go ahead.
I'm Joey Pasterski from the University of Illinois at Chicago. It sounds like a lot of the GCMS and LDMS experiments will be sort of force intensive, and same with drilling. So for kind of lack of a better term, before you want to do some of an analysis, you're going to want to kind of poke something with a stick. So then what's like your analytical stick that you're poking before you actually do drilling and analysis?
Sure. So the plan is to utilize the entire payload to understand a landing site before we make the choice to drill. So that includes all the imaging that we'll have, as the context of where we're located. Are we did we land in a plinth of dune material? Are we sitting on ice? Then even the microscopic imagers are pointed to the areas where the drill would drill, and so all of the information we can gain from that. As part of the DragMet instrument package. And so we'll be understanding things like surface porosity, dielectric constant, a lot of information just that we can get from that. And then, of course, we have the gamma ray neutron spectrometer dragons, which will give us the bulk elemental abundance around the lander. So all of those things will be employed at each landing site to best understand the surface, to make a decision. The two things we'll always be asking is it safe to drill? And then, of course, as we go from site to site, it may be that we have moved and we're in a new location that is giving us almost exactly the same information. So we probably haven't left that geologic unit, so it's probably not quite worth it. And that's the valuable question about drilling. And then if we make the decision with all of that data that we want to give it a shot, we'll have, as I mentioned, an interrogation drill where we'll do just a little pilot drill hole to get an idea of how the material responds to drilling, and then we can do the detailed imaging and what kind of particles there are, and even look for things like, does it glint a little bit? Do we think it's wet? Because we may not want to sample something wet because it's more likely to be sticky. So all of that kind of information will go into deciding to proceed with a sample. And then even once we do that, the way that the mass spectrometer operations are designed is that we'll always start with an LDI measurement, a laser absorption measurement, and that will be our first assessment of the composition. And that information will then also come back round in the loop to make a decision, do we go on to GCMS, which is the most resource intensive of the options. So that's all going to play out during our surface operations. It's going to be very exciting.
Super exciting. Thank you.
Thanks.
Hi, I'm Martin Cordner from NASA Goddard. I was wondering if you have a sense for the ages of the materials you'll be sampling, given the ongoing precipitation of organics from the atmosphere and the possibility of exposing older surface materials by erosion from liquid.
Sure. I think one of the most exciting capabilities of our mission is our ability to sort of follow up on things we see. So when we do imaging, we're hoping we'll be able to see things like different geologic units outcropping, or perhaps exposed in crater walls or other places, different individual geologic layers that we'll be able to identify and then be able to sample the material that's fallen out of them by flying over to it and getting to it. So we won't be able to get absolute ages, obviously, because we don't have a radioisotope dating system that we know will work on Titan. We don't carry one with us, but we hope to build up a picture over time of what the geologic history of the area has been based on structural relationships and outcrops, and being able to follow up on what we see and fly over and investigate what we need to be able to build up that picture over time. So we won't be able to do that, right in one single observation, but we hope over the course of the mission to be able to build up a sense for, the ages of the various material we're
I guess I just had this naive impression that that there's a lot of particulate precipitation. So does that tend to bury everything, or it gets washed away?
So, for instance, the Huygens probe had measured this when it came down. The penetrometer went through some material, and it was estimated to be about 7 millimeters thick. So there was a coating at the Huygens landing site, 7 millimeters thick, and that's one of the reasons we have a drill that will get us down 6 centimeters, so that we'll be able to get through any surface mantling. It seems that either rainfall or aeolian processes are keeping it cleaner, so that we don't have meters of this stuff building up. And we have the drill to be able to get us through what we think is a pretty thick but not impenetrable veneer of material that's falling out of the atmosphere.
Yeah, and it really is a relatively, over kind of longer term timescales, a relatively active environment with aeolian processes, moving materials around and clearing some areas, and rainfall as well. So we expect there clearly isn't, we know from the data from Cassini and from Huygens, that there isn't just a uniform layer that's built up. There are a lot of places where that's been moved and modified too.
All right, you get the honor of the last question.
Oh, wow, wonderful. And this last question will be a very analytical chemistry question, so apologies in advance. But I'm curious about the capacity of the mass spectrometer to really identify molecular compositions. So you were talking about an interest in nucleobases, and I'm sure, as you're well aware, with compounds of that nature, there are many possible compositions you could have for a given mass number. And so I'm curious, will the instruments be able to resolve like isotopic windows, or be able to do fragmentation to be able to try to go beyond just mass number and get more detailed information about molecular composition?
Yes, so you,
Keep going.
so particularly in the laser absorption node, oh, is it not working yet?
You want to come up here? Oh, okay.
Sorry. Okay. So, sorry. When we're operating the laser desorption mode, we definitely plan to do MSMS. So the idea is that we have the capability to isolate the mass window and then do fragmentation to look at the components of the molecules that we're isolating. So that's one of the ways that we'll be doing that kind of deconvolution, like you said, moving kind of beyond a single mass unit. And then, of course, one of the reasons as well that we carry the GC and the GCMS mode is that enables a different type of separation step by looking at retention times and how things, and separating them out, and how things elute, and then the spectra that we see there and how they respond to derivatization, if that's what we're doing. Then we'll use that also as a way to identify molecules.
Sorry, we can't. Okay. Can you go?
Laser desorption can do MSMS. Is that right?
Can you say that again?
Yeah.
I couldn't hear.
So the GC can do GCMS, and the laser desorption can do MSMS. Is that?
That's right. So that's the primary plan. Yes. Mm-hmm.
Awesome. Well, thank you guys so much for joining us. The discussion doesn't have to end here, because we're going to be all around all the rest of today, and some of us around even tomorrow. And we hope to continue this discussion throughout the year. I want to thank all of our panelists, including the fantastic Ken Hibbard, who is called in all the way from Maryland. And of course, our PIs, Ibby Turtle, and deputy PIs, Jason Barnes and Melissa Trainer, as well as the other Dragonfly team in the room. Thanks to all of you. We are really excited to start taking data and making some cool discoveries with you in the 2030s.
Thank you.